Hello, in this lesson we will learn about symmetry. The learning goals are to identify line or reflectional symmetry and rotational symmetry. A figure has reflectional or line or mirror symmetry if you can draw a line or axis of symmetry through it, like we're doing here. We're drawing a line or axis of symmetry so that the figure on one side of the line of symmetry is a reflection of the figure on the other side of the line. So we can see that the left side and the right side of this butterfly are mirror images of each other. So if we do a folding, this half will perfectly overlap with the other half because it's a reflection. So that's what a line of symmetry is. Basically, every point on one side of the line has a corresponding point on the other side of the line. A figure can have more than one line of symmetry. For example, this snowflake has 1, 2, and 3 lines of symmetry. Now let's check horizontal versus vertical line of symmetry. Does the letter A have a vertical line of symmetry? Let's analyze that. So this is capital A, and we're going to draw a vertical line that passes through the very middle of A, and we're going to split it so we can appreciate that the left and the right parts are mirror images or mirror image halves. So yes, the vertical line is a line of symmetry because it separates both halves that are exactly mirror images of each other. Now, does A have a horizontal line of symmetry? We draw a horizontal line through the very middle of A, we split it, and we can appreciate that no, this horizontal line does not create two mirror images because the top and the bottom parts are different. They are not mirror images of each other. If we fold one onto the other, they won't match. Now, a figure can also have rotational symmetry. If you can rotate a figure between 0 and 360 degrees, and the resulting figure is the same as the original before you complete the 360-degree rotation. For example, we have an equilateral triangle. We're going to mark the vertex with a red circle, so we have a reference point. Now, we're going to rotate that, and we see that after a 120-degree rotation, the triangle looks the same as the original one. Then if we rotate 240 degrees, the triangle looks the same as the original one. And finally, if we rotate 360 degrees, the triangle looks the same as the original one. All figures will have this type of property. If we rotate 360 degrees, any object, they will look the same. That doesn't mean they have rotational symmetry. They have to look the same before you complete the 360-degree rotation, like this triangle. This triangle looks the same twice before reaching 360 degrees, so it has rotational symmetry. Okay, so the equilateral triangle has rotational symmetry because at least once before completing the 360-degree rotation, it looks like the original triangle. In this case, twice, right? After 120, and then after 240 degrees, it looks the same as the original one. Now, the order of rotational symmetry for this triangle is 3, because 3 times during the 360-degree rotation, the rotating triangle is identical or matches the original one, right? 1, 2, and 3. So 3 times during the 360-degree rotation, this triangle matches the original one. So the order of rotational symmetry is 3. The order of rotational symmetry is the number of times an object fits onto itself while being rotated through 360 degrees. The angle of rotational symmetry is the smallest angle the object can be rotated to coincide with itself. To get this angle for this equilateral triangle, we first draw a circle, a circumscribed circle of the triangle, basically a circle that passes through all the vertices. Then we draw the center of the triangle, which is also the center of the circle, and we connect the center with the vertices of the triangle. Now we know the whole circumference is 360 degrees. Since we're dividing that 360 degrees into 3 equal parts, 1, 2, 3, each angle is going to be 360 divided by 3, which is 120 degrees. So basically, the angle of rotational symmetry for this equilateral triangle is 120, because 120 degrees is the smallest angle it can rotate to look the same as the original triangle. So for all regular polygons, you divide 360 by the number of sides of the polygon, and you will get the angle of rotational symmetry. Now, we're going to analyze the symmetry of a regular pentagon. This is a pentagon. It has 5 sides and 5 vertices. Now, the question is, how many lines of symmetry does a regular pentagon have? It will have 5 lines of symmetry. The first one going through the first vertex. The second one goes through the second vertex, and again, all of them going to the midpoint of the opposite side. The third one, the fourth one, and the fifth one. So the number of lines of symmetry for a regular polygon equals their number of sides or their number of vertices, which is the same. What's the order of rotational symmetry of a regular pentagon? Again, we mark this regular pentagon with a circle as a reference point, and we rotate it 1, 2, 3, 4, and 5. So 5 times during the 360-degree rotation, the pentagon, the regular pentagon, looks exactly the same as the original one. Therefore, their order of rotational symmetry is 5. What is the angle of rotational symmetry of a regular pentagon. Again, we draw a circle just to indicate that this whole thing is going to be 360 degrees. We draw the center, and we connect the center with the vertices of the pentagon. So basically, we're dividing 360 in 5 equal angles. So each angle is going to be 360 divided by 5, which is 72 degrees. So this regular pentagon, after it rotates 72 degrees, it will look exactly the same as the original one. Therefore, that's the angle of rotational symmetry for this regular pentagon. Now we are going to analyze the symmetry of a general parallelogram. Here we have a general parallelogram. The question is, does it have a line of symmetry? For example, is this blue line a line of symmetry? To analyze if the blue line is a line of symmetry, we're going to make the blue line a vertical line because it's easier to analyze it when the line is either vertical or horizontal. So let's make it vertical by moving the parallelogram like this. And we're going to color both halves of the parallelogram, orange and green. And we're going to reflect this green triangle, and it will look like that, the reflection. So we can see that the reflection of this green triangle does not match the orange one. Therefore, the green and orange triangle are not mirror images of each other. Therefore, this blue line is not a line of symmetry. Let's draw another line, this red line, and let's see if these two halves are a reflection of each other. So again, we're going to make the red line a vertical line to analyze it, like this. We're going to color both halves, yellow and orange, and we're going to reflect the orange half, like this. So we see that the orange reflection does not match the yellow part. Since they don't match, they are not a reflection of each other. Therefore, the red line is not a line of symmetry. A general parallelogram does not have a line of symmetry. However, it has rotational symmetry. If we rotate 180 degrees, it looks like the original one. Thank you very much for the attention.